Hello, and welcome back to a video series on MAC 2311 Calculus 1. My name is Sean Perry. These are guided notes number 2 in the series, Graphical Limits. Today we're going to be looking at some exercises using graphs to interpret limits. Let's go into a little more detail about how we should go about interpreting limits by purely graphical means. In other words, if we only have the graph of a function, can we interpret various kinds of limits? I'll try to give you some information about the function whose graph we're looking at, but we really are going to look at the graph itself to interpret the limit. Now, the examples you're going to see below are going to be characteristic of the kinds of problems you'll see in your homework. However, I should provide the caveat that I'm not going to just do your homework with different numbers. This would in fact be counterproductive to what we're trying to accomplish in an advanced math class. You're also going to want to know how to handle functions you haven't seen before. I will try in the course of this class to give you some of those problems, but it will not be exactly the same, and that is by design. You shouldn't think that that is a bug. It is in fact a feature. Let's begin with one of the most common examples of functions which give us non-trivial limits, what are called piecewise functions. Piecewise functions are functions which have different rules for different intervals of inputs. When x is inside of a certain interval, we're going to calculate our output using different rule sets. This should be familiar to you from some standard classes in, say, the college algebra level, but we're going to take it up a notch in calculus. There's going to be more rules, and you're going to have to think about how the limit would apply to especially the junctures where we change rules. Let's look at some examples. So here we have an example of a function f of x, who is defined as follows. It's 2x plus 10 when x is less than negative 5. If x is equal to negative 5, the value is negative 2. If x is between negative 5 and negative 2, the value is 2. And when x is between negative 2 and 0, the value is also 2. Please note that I just left out the value negative 2. If no value is given for the function, you should interpret the function as not being defined at that point. Continuing on, when x is equal to 0, we're going to give it the value of 1. And when x is greater than 0, we're going to have the line negative 2x plus 2. As I said in the introduction, we are mostly focused on a graphical interpretation of limits for this section. So this list of rules here is really only there to provide you with a concrete example of how this graph was constructed. All of the questions I'm about to pose may be answered from this graph alone. Notice that we have our line negative 2x plus 10. Then we have this constant value of 2 between negative 5 and 0, with negative 2's value left out. Now, values left out are indicated by open circles. Closed circles indicate a function value at a point. So here at negative 5, we are given the value of negative 2. And here at 0, the function has the value of 1. Here at negative 2, there is no value, it's undefined. And for positive values, we can see it has the graph negative 2x plus 2. So now let's ask some questions about limits. But before we do, it might be a good idea to test our knowledge about piecewise functions by answering these questions about the function values at various points. F of negative 5, we find right here. It's given on the graph as this dot, which has a value of negative 2. At negative 2, there is no value. So I'm actually going to erase the equal sign here. And we could either put undefined, or we could put does not exist. Now, if your homework says write DNE, write DNE. If it says write undefined, write undefined. It really is a quite slight shade of meaning between the two of those. Now, f of 0, we have right here on the graph. We can see the filled in circle there at 1. So this has a value of 1. And f of 1, I wanted to give at least one point that's from a sort of regular point on the graph. That is to say, if I look at x equals 1, the y value is 0 right here. It's just a part of that line. But there's no reason that I couldn't then answer the question that f of 1 is equal to 0. Now let's do some questions involving left, right, and two-sided limits. When we consider the point negative 5, if we approach it from one side, let's begin by approaching it from the left. That is to say, looking at this exponent that has a little negative sign in it, we're going to approach it negatively. So starting from values less than -5, we're going to get closer and closer to -5. And what do the corresponding y values get closer and closer to? Well, as we approach from the left, we're getting closer and closer to 0 for a y value. On the other hand, if we consider approaching positively, that is to say from the right, we're going to have values just greater than -5. And as we get closer and closer to -5, what do the y values do? Well, it's a constant function at that point, so you're getting all 2's as you approach from the right. So your right limit, your limit as we approach positively, is going to be 2. Now, notice that these are not equal to each other. 0 is not equal to 2. When the left and right limit don't match, we would say the two-sided limit does not exist. And so I'm going to erase this equal sign here, and I'm going to write does not exist for my two-sided limit. Remember, the two-sided limits don't have a plus or a minus in the exponent here. They just say x approaches -5. And so for this, I would write DNE, does not exist. I don't like to say that it equals does not exist. I also don't like to say that it equals undefined, because equals should be reserved for numerical values. When something has a numerical value, we can say it's equal to or not equal to something. But when it has no numerical value, I feel a little funny about saying it's equal to that. Okay, so moving on to -2, let's consider what happens as we approach negatively, that is, from the left. So going to -2 for my x value here, I'm going to take a look at what happens as we get closer and closer and closer from the left side, that is to say, from values less than -2. Well, the y values are all constantly +2. And so because they aren't changing, they are getting close to 2 and staying close to 2 because they're equal to 2 the whole time. So as we approach -2 for an x value, the y values are constantly 2. So our limit, as we approach from the left, is going to be +2. And likewise, as we approach from the right, our y values, they are approaching 2. Now, when these two left and right limits are equal to each other, we then have a defined two-sided limit, or the total limit, or just the limit, if you like. That's going to be 2. Okay, so now we're going to approach 0 negatively. So we start from values less than 0 and get closer and closer. And then we look at the corresponding y values, and they're getting closer and closer to 2. They're constantly 2, in fact. As we approach 0 positively, that is to say, from the right, we no longer have a constant function, but our values for y are getting closer and closer and closer again to a value of 2. So this is also a 2. These being equal to one another lets us know that our two-sided limit is defined and is equal to 2. Something similar is going to happen when we approach 1 negatively. So that's approaching from this side. We get y values that get closer and closer to 0. Likewise, for approaching 1 positively, we get closer and closer to 0 again. And these two being equal to one another lets us know that the two-sided limit is equal to 0. Again, remember that if they are not equal, then your two-sided limit will not exist. Let's have a look at another piecewise function. This one is composed of a variety of elementary functions. When x is negative, we're going to look like e to the x. When x is between 0 and 1, we'll look like 1 over x. When x is equal to 1, we'll take on the value of 0. And when x is greater than 1, we're going to look like cosine of 2 pi x. Let's start with addressing some questions about the function value at various points. You might notice in the instructions, I haven't actually said what to do when x is equal to 0. And as before, if that's the case, we're going to treat this as undefined. So I'm going to erase this equal sign here and just write undefined. On the other hand, when x is equal to 1, we're over in this region. We have this solid dot at 0. So when x is equal to 1, f of x is equal to 0. What about 4? Well, 4 is greater than 1, so we're using this rule set. And plugging in 4 here, you can see I have cosine of 8 pi, but I said we would be able to use the graph. If we take a look at 1, 2, 3, 4, here we are, and looking right here, I can see that it has a value of 1 at that point. This last one is a little tongue-in-cheek because I made it go off the edge of the graph. What I want you to think about here is, what's the pattern for cosine of 2 pi x? How does that relate? How can we extract that from the graph? And notice that at the halfway marks, here's 1.5, here's 2.5, here's 3.5, and so on. We're getting -1 every time. We should be able to extend the pattern that we see here and notice that at the 1/2 markers, the graph is always -1. And that's going to be true at 50.5, just as it is at 1.5 and 2.5. So this is going to be -1 here. Okay, but now let's get to the limits. What about my approach of towards 0 negatively? Okay, so here we are, negative to 0, getting closer and closer. And our y values are then getting closer and closer to 1. On the other hand, if we take a look at values greater than 0 and getting down towards 0 from the right, well, our y values here are going to be getting bigger and bigger without bound. What happens to 1 over x as you go towards 0? Well, the smaller the value is that you plug in to the denominator, the greater the value of its reciprocal. And that pattern doesn't change. We just keep growing without bound the tinier a number that we plug in. This is when we would say that the limit is equal to infinity, positive infinity, because our graph is shooting off towards positive infinity. We should know that we have a vertical asymptote here, right? When graphs look like they begin to hug a vertical line and approach it without crossing it, that's when they are going to be shooting off to either positive or negative infinity. This one's going up, so we interpret that as a limit of positive infinity. Again, we note that these are not equal to each other, and that means that the two-sided limit, the total limit, or just the limit, if you like, does not exist. I'm going to erase that equal sign and write dne. Okay, let's move on to the value of 1. If we approach 1 from below, our graph is getting closer and closer to 1 itself as a y value. Likewise, if we approach from above, x values greater than 1 getting closer and closer to 1 from above, our y values are getting closer and closer to positive 1 as well. And because these two are equal to each other, the limit is also equal to 1. Now let's look at some limits as x approaches negative and positive infinity. When x approaches negative infinity, we want to think about what is the trend of the graph as we go off the edge of the map to the left, right? Down here, this is where negative infinity is lurking. And so we want to think about what is the graph doing as we get values that get smaller and smaller, or I should say have greater and greater magnitude, but in the negative direction. And you might know about e to the x, but you should also see on this graph that we're starting to get closer and closer to the x-axis. That is to say, we have a horizontal asymptote here. If we were to continue this graph, it would just continue to get closer and closer to the x-axis. So when we have this kind of horizontal asymptotic behavior, we have something that we are getting closer and closer to as x goes towards negative infinity. And that value is 0, the y value that you have on the x-axis. On the other hand, what happens as we go towards positive infinity? Well, that's cosine, that's wiggling back and forth without ever ending. It never settles down and gets closer to and stays close to any one particular value. It just bounces back and forth between -1 and +1 forever. And so there is no limiting behavior as we go off the edge of the map towards positive infinity. It just wiggles back and forth between -1 and +1. And so there isn't going to be a limit as x approaches infinity. This is again going to be the kind of situation where you would say the limit does not exist. So we've seen now our two characteristic situations of where you don't actually have a limit. You don't have a limit if it approaches two different things from the left and right, and you don't have a limit if the value never settles down and approaches one single value. That should do it for examples of piecewise functions. Let's move on to rational functions, that is, quotients of polynomials. So to the right, we have a graph of a rational function, and I gave its definition over here to the left. Here you can see that I have both the unfactored version and the factored version of the denominator. I'd like to just point out that at some point in time, I would like you to be able to make the transition between the unfactored and factored form using some of your tricks that you may have learned in your pre-calculus class about how to reduce a larger polynomial, factoring the greatest common factor, dividing by the obvious roots, or in this case, the poles of the function. That is to say, where do we see vertical asymptotes? But for now, we can get by just answering the questions based on the graph. Note that we have these two vertical asymptotes, one at -1 and the other at +1. And we have a hole in the graph at 0, 0. That is to say, if we were to cancel the x from the top and bottom here, we would find ourselves with a hole rather than a y-intercept at the origin. Notice as well that we have two different characteristics of the vertical asymptote. The one at -1 is split and has one branch going towards positive infinity and the other going towards negative infinity, while we have a one-directional asymptote at +1, where they both seem to be swooping upwards. Let's take it from there. If we consider approaching -1 from values less than -1, then we're approaching x values as such. Then our y values are swooping off towards positive infinity, getting larger and larger without bound. On the other hand, if we approach from values above -1, then the corresponding y values descend downwards without bound. In other words, they go towards negative infinity. We note these are, in fact, not equal to each other, at least in the current context, and so we would say this limit does not exist. Now, if we look at values just less than 0, approaching 0 from below, our y values are also approaching 0. And likewise, for values above 0, the corresponding y values get closer and closer to 0. These two values are, of course, in fact, equal to each other, and so our two-sided limit has a value of 0. If we consider the x value of 1, approaching it from below, we get y values that go off towards positive infinity. But that's also what happens if we approach from values above 1. These y values also go up to positive infinity. Because these two are equal to each other, the total limit is also infinity. Now let's consider what would happen as x approaches infinity and negative infinity. As x approaches infinity, we see that it is getting closer and closer to this horizontal asymptote. If you remember some properties of rational functions, you could also see that happens because the degree of the top and the degree of the bottom match, and their ratio of coefficients is equal to 1. But it should also be clear from the graph, I will draw a little dotted line when we're dealing with asymptotes. So this limit, as x approaches infinity, the y values it's getting closer and closer to is 1. And likewise, as we go towards negative infinity, right? If we imagine x values getting smaller and smaller without bound, we're getting closer and closer in our y values to this horizontal asymptote. And so this will also have a value of 1. We don't usually think about left and right-handed limits for infinity because you can really only approach infinity from below, and you could really only approach negative infinity from above. All right, let's move on to another example. Let's talk about a new kind of function, one that you may or may not have seen in your previous math classes, the floor and ceiling function, two of the so-called rounding functions. These functions round down or round up a number respectively. For example, you can see here for the floor function, which has a symbol that looks like a little floor for x, we have every integer keeping their value. So for example, 0 is still 0, but values just larger than 0, between 0 and 1, are rounded down to 0. When we get to 1, we keep the value of 1. So notice there's a solid circle here and an open circle here. And then continuing on for values just greater than 1, we round down to 1. So for example, 1.5 here would get rounded to 1. So we have constant functions between the integers and then these jumps making a little staircase. And similarly for the ceiling function, whose symbol looks like a little ceiling for x, you're going to keep the value of each integer. So 0 is still going to 0, but values just larger than 0 are rounded up to 1. And then they keep that value until they get to 1, and then values just larger than 1 are rounded up to 2. So 1.5 here gets rounded to 2. And so on up and down this graph here. And so these are actually a very interesting kind of function to compose with other functions, and you can get some pretty interesting graphs out of that sort of have the same property of jump discontinuities. While these are interesting functions in their own right, What we're really interested in is composing them with the elementary functions. And by elementary functions, I mean things that you've studied in your algebra class, like the polynomials, the rationals, exponentials, radicals, abs-vals, trig functions, and so on. No special weird functions here, but we're going to take these floor and ceiling functions and sort of stick them into the elementary functions to create some kind of neat looking graphs. So for example, let's take a look at the function where we've stuck into the ceiling function 1/2 x squared. So we're going to take the values that 1/2 x squared gives us and round those down to their nearest integer. Now, between, say, square root of 2 and negative square root of 2, these values, when you plug them in, are going to give something less than 2 when you square them, and then 1/2 of that will be less than 1. So if we round down all those values, we'll get 0, which is why this line is flat here at 0. But again, we're not worried about plugging things in. I just want you to have an explicit function that goes on with this graph. We can read off what the value of the graph should be by looking at the graph itself. So for example, when we ask what is f of 2, when we look at 2, we see that it has a value of positive 2 when x is equal to 2. And so this is going to evaluate to 2. When we approach 2 negatively, that is from below, we start out on the y equals 0 part of the graph. And then before we get to 2, we find ourselves at the y equals 1 part of the graph. So here we're getting closer and closer to this value of 1. But if we approach 2 positively, so starting over here with our x values and working our way down, we start off first at this higher part of the graph, these y values that I picked. Then we jump down here and we get closer and closer to this value of 2 as we get closer to an x value of 2. So in the end, our y values are approaching 2 at this point. Now, these are not equal to each other, and so we would say that this limit does not exist. To reiterate an important takeaway from the previous video, we noticed that jump discontinuities generally result in the non-existence of the two-sided limit. Now let's move on to talking about trig functions, or better yet, some fun compositions of trig functions with the elementary functions. Later on in the course, I'm going to give you a proof of the following fact, that the limit as x approaches 0 of sine of ax divided by ax is equal to 1. But until that time, we'll take this as a fact and look at the evidence for that fact from the following kinds of graphs. So over here to the right, I've given the graph of f of x equals sine of 10 pi x divided by 10 pi x. You can see it has some really cool wiggling behavior, just like sine does, but because it has a 10 pi x in the denominator, as x gets really large, we have decreasing amplitude. Now, you might think that dividing by x should send this sucker to infinity as we go to 0. But remember, sine of 0 is also 0. So something is balancing out that zeroification of the denominator by putting a 0 in the numerator. And we're going to see that explicitly later on. I will note that it is an open circle here. And so f of 0 isn't really equal to anything. We are dividing by 0 at that point. And so we should just say that it's undefined. We should recall from our algebra classes that this has always been a big no-no. You cannot divide by 0. If 0 has a reciprocal, lots of weird stuff happens that gives us contradictions that render a kind of explosion where we cannot really use math anymore. And so we have to let division by 0 be undefined. But even if we didn't know what the function was that we'd been given, we could still say that this was undefined by looking at the open circle in this graph here with no solid circle anywhere in view. That also tells us that there is no defined value for the graph at 0. But we do have a pretty well-defined limit process here. If I go from values lower than 0 and get closer for my x's, my y values are getting closer and closer to 1. And likewise, as I approach from above, values of x that are positive getting closer and closer to 0, my y values also are getting closer and closer to 1. These two are equal to each other, and so we have a two-sided limit of 1. What about our limits as x approaches infinity and negative infinity? Well, if we look over here, we can see that we have this oscillation, yes, but we also have decreasing amplitude. It's getting closer and closer to 0 as we go off towards positive infinity. And likewise, as we go off towards negative infinity, we also have this decreasing amplitude of oscillation. And that's because we're dividing by larger and larger values, something like sine of x, which is pinned between -1 and +1. And so we also get a 0 on this side as you approach negative infinity. So I just want to note here that discontinuities at a point, like at 0 only, are often called removable discontinuities because a new function could be defined to have a value at that troublesome spot. We just set that value equal to its limit. So in general, if you had a function not defined at c, but its limit was defined at c, you could build a new function that fills in the discontinuity by saying, well, it's equal to f of x everywhere else, but at c, it's equal to its limit. So for example, we could have filled in this empty circle here by saying, let's let it be sine of 10 pi x over 10 pi x everywhere except for 0, but at 0, let's let it have its limit value of 1. That would fill in the empty hole and give us a continuous function. We'll talk more about continuity later, but we should note that for these point discontinuities, where we can totally fill in the discontinuity with a reasonable value that sort of plugs the gap, we do have a well-defined limit. So using that well-defined limit, we could plug in the hole in the graph. That's why they're called removable discontinuities. All right, let's move on to another species of function. Now let's see what kind of fun we can have with exponential functions. We're going to be interested in seeing what we can do to play with the exponential function by composing it with other function types. See what kind of interesting behavior we can get. And again, we're looking at the graphs in this section, but you should test your intuition here. Ask what would happen if you plugged in big positive or big negative numbers to your exponential values. Could you predict what the graph will tell you? Does it make sense still? So as an example, let's take the function f of x is equal to the quotient of 2 minus e to the x with 1 minus e to the x. So let's think about what happens with this graph as x goes to infinity. And we notice that as x goes to positive infinity, we think about x is getting larger and larger, our y values are getting closer and closer to this horizontal asymptote at 1. And likewise, as we get smaller and smaller for our x values, with larger and larger negative values, with larger and larger magnitude, that is to say, bigger and bigger negative numbers, your y values are getting closer and closer to this limiting value at -2. And again, test your intuition out. Make sure that makes sense. What happens if you plug in a really big number into e to the x? We'll get something that goes off towards infinity, but we'll also get that same thing in the bottom. And the 2 and the -1, they're going to be almost inconsequential compared to the values of e to the x. And so we wind up with something essentially just negative e to the x over negative e to the x. That's why we see a limiting value of +1 as we go towards positive infinity. Now, on the other hand, your negative x's plugged in here, if we had really big negative numbers for x, well, remember, e to the x has a tail in that direction, a horizontal asymptote at 0. And so you really wind up with just zeros for your e to the x's, which gives you a ratio of 2 divided by -1, which is why we see a -2 down here for our horizontal asymptote. Note that these values we get as x goes towards positive and negative infinity, if they're equal to any number, then they are indicative of horizontal asymptotes. But now, as opposed to the rational functions, where we usually have the same number as our horizontal asymptote, here's a function that just gave us 2 different horizontal asymptotes, a left and a right one. And that shouldn't be too surprising, considering that e to the x has very different behavior as x goes to negative infinity as it does to positive infinity. Remember, e to the x only has a horizontal asymptote in one direction on the left side. On the right side, it goes off towards infinity. So we've already seen examples of functions who have different behavior for their horizontal asymptotes on the left and right, but now we have one that gives us 2 finite values, different values, as we go towards negative or positive infinity, that is to say, right and left horizontal asymptotes. Let's move on to seeing what kind of goofiness we can do with radical functions. Here we have an example of a radical of a polynomial plus a polynomial. If we take a look at its behavior as it approaches positive infinity, it does have a limiting behavior. My y values are getting in closer and closer to 2. On the other hand, as we go towards negative infinity, it seems to drop off the edge of the map. And so we wind up with something like negative infinity for f of x as our x values go towards negative infinity themselves. So similar to the exponential function, this one only has a horizontal asymptote on one side. Okay, now let's talk about the absolute value function and how we can compose that with elementary functions. Let's recall first that the absolute value function can be defined thus. It could be defined as a piecewise function where you have the line y equals x, 45-degree line here, for values x greater than or equal to 0. But then for negative values, we need to flip the sign and make it positive, which is what we're doing with this expression here. So we have this characteristic V shape with our hard corner, and we can plug in absolute value of x into various kinds of functions and get some interesting behavior. So let's see an example of that. Here we have one where I've sort of kind of played with it and made it into a polynomial, although I left this x without any absolute value. So notice for this one, as we go towards positive infinity, my y values are getting closer and closer to 1. On the other hand, on the left side, as we go towards negative infinity, we have values getting closer and closer to positive 3. We can also make all kinds of interesting rational functions out of absolute values. So for example, here's absolute value of x cubed plus 1 divided by x cubed minus 1. Now you might know this has a 0 in the denominator at positive 1, and so we shouldn't be too surprised to see a vertical asymptote there. What I really think is cool about this graph is that we actually have constant behavior followed by rational function behavior around 0. So, but how is that going to really affect the limit? Not so much, but let's talk it out. So if I think about approaching 1 negatively, right? I'm approaching from the left. My y values are going down without bound, so we get negative infinity. It's a split asymptote, meaning as I approach from values positive, we are instead shooting off towards positive infinity. And these are not equal to each other. And so we wind up with a two-sided limit, which does not exist. Our values as x approaches infinity, well, on this side, we get bigger and bigger, and our y values get closer and closer to positive 1. And we have the normal asymptotic approach as we go in that direction. That is to say, this graph seems to get closer and closer without touching 1 on the right-hand side. But look about on the left-hand side here, right? If we go towards negative infinity, we have constant behavior. It's constantly 1, or I should say it's constantly negative 1, because that would make absolute value equal to negative x cubed, and that's just the negative of the denominator. And so they would cancel to negative 1 constantly. So we have a negative 1 for our limit as x approaches negative infinity, but it's of the kind where y is a constant value, rather than the limit as x approaches positive infinity, where we're getting closer and closer to 1 without actually ever getting there. So cool stuff from the absolute value function. And that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.